Welcome to the Deep Dive. Today we're tackling really the biggest story right now in advanced computation, Google's Willow Quantum Chip. We've pulled together the sources, and our mission is to unpack what this huge step, this first ever verifiable quantum algorithm on hardware, what it actually means for, well, for everyone.
Absolutely. For so long, quantum computing felt like potential, didn't it? Always if and
Yeah.
maybe. But this Willow achievement, it really shifts the conversation. It's much more about how and when now. This isn't just, another lab result. It feels like a genuine pivot point.
Exactly, that headline phrase is key. First ever verifiable quantum algorithm on hardware. We've heard supremacy claims before, but verifiable sounds
Mm-hmm.
different, more solid.
It is different. It signals, I think, a really crucial strategic shift. It confirms we're actually on the path to real-world uses, things like medicine, designing new materials, fundamental chemistry,
Right.
areas where, frankly, classical computers just hit a wall.
Okay, let's start with the number that grabs you because, wow. Willow ran this quantum echoes algorithm 13,000 times faster than the world's top supercomputers. That's not just faster, that's, well, it's almost a different category of computation opening up, isn't it? It really is, and verifiable advantage here means a couple of things,
Yeah.
importantly. First, the speed up has to be solid, repeatable. You can check the working. Second, the problem it solves has to be genuinely out of reach for the best classical methods we have today. Not just tricky, but practically impossible.
All right.
And getting it published in a top journal like Nature, which happened October 22nd, 2025, that's the scientific stamp of approval. It says, okay, a real barrier has been broken here.
So if Willow is the engine, this quantum echoes algorithm is like the, I don't know, the high-octane fuel. How does it work? The descriptions sound pretty intense. Strategic perturbation, reversing quantum evolution. Well, let's simplify it a bit. Think about the quantum nature of the qubits. They can be in multiple states at once. Tangled up, we use that. The algorithm basically sends a signal into these qubits. Then very carefully, it nudges just one of them, a tiny, precise disturbance. And then this is the clever bit. It reverses the whole quantum process, runs it backwards in time, essentially.
Versus it, what does that achieve?
That reversal acts like an amplifier. That tiny initial nudge gets magnified massively. It creates this detectable interference pattern, like an echo bouncing back but carrying information. That echo tells you about the structure of the system the signal interacted with. It's an incredibly sensitive probe.
I loved the analogy in one of the sources for this. It's not just spotting a wreck on the seabed.
Right.
It's being able to read the nameplate on the hull, that level of detail.
Exactly that. And that level of detail, that's where the real scientific impact lies. It lets you see structural details, maybe in molecules or materials that were simply invisible before. You're moving beyond just general properties to mapping the intricate internal setup. That's game-changing for science.
Okay, so the algorithm is incredibly powerful. But that kind of speed and precision, it depends entirely on the hardware being reliable, right? Speed's no good if the machine keeps making mistakes. Let's talk about Willow itself. 105 superconducting qubits, an advanced 7x7 grid, but the fidelity numbers, the precision, that seems to be the real engineering story here.
Oh, absolutely. Those numbers are crucial. For anyone not deep in quantum, fidelity is basically how often the processor gets the calculation right. Its success rate, Willow hit 99.97% for single qubit operations. That means only about 3 errors in every 10,000 operations. Really impressive.
And the two qubit operations, the entangling gates, those are harder but just as vital, and they're also very accurate.
Yes, 99.88% accuracy for entangling gates. Entanglement is where the quantum magic happens, linking qubits together. Doing that reliably is tough. And achieving that precision while performing, what was it, over 1 trillion quantum measurements in just tens of seconds, that demonstrates real computational power combined with stability. It's not just fast, it's fast and controlled.
But the big ghost-haunting quantum computing has always been errors, especially when you try to scale up.
Yeah.
More qubits historically meant way more errors. How did Willow tackle that fundamental challenge?
This, for me, is maybe the single most important technical breakthrough mentioned in the sources. For, 3 decades, the problem was. Add more qubits, and the error rate shoots up, often exponentially, made bigger systems kind of useless. Willow demonstrated the opposite. It showed exponential error reduction as you add more qubits.
Whoa, hang on. Exponential reduction. That sounds like it flips the whole problem on its head. How does adding more stuff make it less error-prone? That seems counterintuitive.
It does, right. But it's down to really clever system architecture and reaching those high fidelity levels we just talked about. It's like, imagine building a bridge. If you just add more beams randomly, it might get weaker. But if you design it intelligently, Adding components in the right way with the right materials and stress management, the larger structure can actually become more stable overall relative to its size. Willow's design, combined with sophisticated error mitigation built in, means the system's coherence holds up better even as it gets bigger and does more work. This fundamentally changes the roadmap for scaling up to, say, 1,000,000 qubits.
Okay, that distinction is critical. It really reframes Willow not just as a one-off success, but as a key step on Google's quantum AI roadmap. This wasn't out of the blue.
Not at all. It's a very logical progression if you look back. Remember 2019, Sycamore, that was the quantum supremacy demonstration.
Right, proving a quantum computer could beat a classical one, but on a very specific, almost contrived problem, like proving the engine could turn over.
Exactly. Then the focus shifted. 2023 saw that error correction prototype. And crucially, 2024 brought Willow with its below-threshold error correction. That was the enabler for genuinely scalable designs.
Which sets the stage for 2025. Verifiable advantage. So, Sycamore proved the concept, Willow proves it can do something specific and scientifically valuable. The focus shifts from, can it run, to what useful work can it do?
Precisely. From theoretical proof to practical utility, even if specialized utility for now.
So let's zoom out then. What does this useful work look like? Where will you, the listener, likely see the impact first?
Well, the potential is huge, but the immediate applications are really exciting. Drug discovery is a big one. Simulating how complex molecules interact is incredibly hard for classical computers. They often rely on approximations. Quantum echoes could potentially let us see those interactions directly. Imagine speeding up drug development from maybe a decade to just a few years.
That alone would be revolutionary. And material science, too, designing new materials from the atom up. Things for batteries, superconductors.
Absolutely. Creating materials with properties we can engineer precisely. That could impact everything from energy storage to, high-temperature superconductors. Big infrastructure changes possible there.
And looking further out.
The vision gets broader. You start thinking about optimizing complex systems for AI, maybe tackling problems in nuclear fusion research, developing next-gen cryptography that current computers can't crack. This capability, this potential is why you see this intense global quantum race heating up. Google, IBM, state-backed efforts. Everyone wants this advantage.
Willow's success definitely throws fuel on that fire. It makes the 1,000,000-qubit goal, the point where we might get truly fault-tolerant machines, feel a bit closer, perhaps. Raises the stakes.
It does, and the strategic implications are massive. This isn't just academic anymore. Quantum computing could disrupt finance, logistics, manufacturing. Plus, the national security and cryptography aspects are huge. Governments and major corporations simply have to pay attention now. The pace is picking up fast.
Now, before we get totally carried away with the future, it's worth pausing, like the sources do, to acknowledge the foundations. This hardware didn't appear from nowhere. The 2025 Nobel Prize in Physics is directly relevant here, isn't it?
Yes, it's a wonderful connection. The prize went to John Clark, Michel Dvorak, and John Martinis. Their pioneering work was on macroscopic quantum effects.
Macroscopic quantum effect. Okay, for those of us who aren't physicists.
Oh, fair enough. It's basically the somewhat mind-bending idea that quantum phenomena, things like superposition, entanglement, usually seen only at the atomic level, can actually be observed and controlled in larger human-made objects. In this case, superconducting electrical circuits. Their work proved you could build these tiny circuits, or qubits, that behave quantum mechanically and hold those fragile states long enough to compute. Willow is built directly on that Nobel-winning science, its theory made real.
A fantastic validation. But let's bring in the reality check. Willow is a huge step. Verifiable advantage is real. But we're not quite at universal quantum computers you can buy off the shelf yet, are we? What are the big hurdles still?
No, definitely not off the shelf yet. The main challenge remains error rates. While Willow showed reduction during scaling, the overall logical error rates are still too high for the really massive universal calculations needed for some of those grander applications. We have a very powerful, specific tool now with quantum echoes on Willow, but not yet the quantum equivalent of a general-purpose CPU.
And just scaling itself, getting from 105 qubits to the millions needed for fault tolerance, that's still a monumental engineering task.
Oh, absolutely. Keeping millions of qubits stable, coherent, interconnected, all at incredibly cold temperatures while making sure every single operation is ultra-precise. It's a huge challenge. Google's roadmap, and others, focuses now on creating logical qubits where you use many physical qubits to make one more robust, error-corrected qubit. That's the path toward full fault tolerance, but it needs sustained innovation.
Okay, so wrapping this up, The core message seems to be, Willow is proof. Definitive proof that quantum computers can solve important problems fundamentally beyond classical reach. It opens a new era, moving from potential to verifiable utility.
Exactly. We've crossed a significant threshold. The race isn't just about building bigger machines anymore. It's about finding useful things for them to do. And that's happening right now, reshaping technology as we speak.
So here's something for you to chew on. The foundational physics underpinning Willow won the Nobel Prize in 2025. That's incredibly recent, highlighting how fast this is moving. So how quickly do you think we'll go from specialized tools like quantum echoes to truly universal, maybe even commercially widespread quantum applications? And perhaps more specifically, beyond the usual suspects like pharma and materials, what other industry do you predict might be the unexpected first adopter fundamentally changed by quantum computing in its daily work?
That's a great question to ponder. The pace is definitely accelerating. The next few years are going to be fascinating.